Welcome back. This is lecture 6. So up until now we have been discussing about ways of making an amplifier. We haven't yet reached that stage yet where we have been successful in making an amplifier. However, we could establish the fact that a linear network was useless to make a power amplifier, right? So we saw that since we need to resort to a nonlinear network, we needed to figure out a way of analyzing nonlinear network. In other words, we needed a way of figuring out how to analyze nonlinear equations. And we know that from our experiences that there are no closed form solutions to a generic nonlinear set of equations, which means that we needed to do some approximations. Another way of thinking about this process is that if you look back at your UG curriculum, undergraduate curriculum, so far you must have noticed that almost everything that you have solved or the curriculum that we are used to are geared towards solving set of linear equations. Even the circuit theory problems that you have solved till now are all linear circuit theory problems. Even the signals and systems courses that you might have taken, which involves Laplace transforms, Fourier transforms, and so on, they all work on the assumption that the system on which the transforms are getting operated on are also linear systems. So given that we have so much exposure to linear systems, set of linear equations, we would like to leverage that existing knowledge to understand how to deal with nonlinear systems also, instead of learning a whole bunch of new mathematics to deal with nonlinear systems, right? So in order to do that, we understood that there are some tricks that we can play. And what were the tricks? The trick was, if we can use numerical methods to analyze the currents and the voltages, or to figure out the currents and the voltages in a nonlinear network once, then we could say that any further perturbation of the network, if the perturbation is small enough, then we could express the subsequent increments in currents and voltages in the nonlinear network as a set of linear equations, right? And that essentially was the genesis of small signal approximations. But we needed to be careful that the small signal approximation is only valid when the signal is really small. Now, what is really small? What is really small depends on what type of nonlinearity that we are dealing with. For example, in the case of a diode, let's say I take a forward bias diode. Let's say the diode is connected to a broader network. I don't know what the network is, but let's assume the network has some voltage sources, some resistors, and whatnot you can think of, right? And let's say this is VDC, and let's assume further that this VDC voltage source has established a voltage of VD across the diode, and let's say the current is ID through the diode. And we have figured out this VD and ID numerically, graphically, using some approximations, right? Then we say that, what if I increase this DC voltage? What if we increase this DC voltage from VDC to plus delta VDC? Then all we can estimate is the fact that this diode voltage would have increased by some delta VD, and the diode current would have increased by some delta ID, right? Now, what is the relationship between ID and VD? The relationship between ID and VD was ID is equal to IS e to the power VD over VT, right? So this is the approximate forward bias diode equation, right? given the knowledge of the voltage across the diode and the current through the diode. Note that I have neglected the -1 term, which means that I am assuming that the diode is sufficiently forward biased. Now what has happened after I have increased the perturbation by delta VDC? The voltage across the diode increased and the current through the diode also subsequently increased, and we did this analysis in the previous lectures. But what I am trying to emphasize here is that is there a maximum delta VD, right? Is there a maximum delta VD or some limit on delta VD beyond which this small signal approximation will break down? So in order to figure that out, we need to understand what is happening with the nonlinear terms as well, right? So let's see what's going to happen now. So now my new current will be ID plus delta ID, right? Which will be equal to IS e to the power Vd plus this increment delta Vd over Vt, right? So if I express this exponential in terms of Taylor series, which is evaluated around the quiescent point Vd and Id, so what should I get? I should get Is e to the power Vd over Vt plus delta Vd, first derivative of Id with respect to Vd, which will yield Is over Vt e to the power Vd over Vt plus delta Vd squared by factorial 2 times the second derivative, right, or double derivative, which is Is over Vt squared e to the power Vd over Vt plus higher derivatives, right? So we know that these two terms are identical, so they go off, right? So what are we left with? We are left with delta ID is equal to delta Vd times this term. So this term is nothing but Id over Vt, right? Plus again delta Vd squared by 2 Vt squared times Id, right? Plus higher order terms, correct? So the small signal approximation that we have been doing till now was only dealing with the fact that if delta Vd is small enough, then I can establish a linear relationship between this delta ID and delta Vd, correct? Which essentially means that I am neglecting this entire stuff, right? As long as these higher order terms are much smaller than the first order term, I should be able to approximate delta ID as delta Vd times a constant, right? Which means that I should be able to replace the diode with a resistor of value Vt over Id, as long as this approximation holds. So what is the limit of this approximation? The limit of this approximation is that this extra term, that if I only take the first extra term, that is delta Vd squared by 2 Vt squared times Id, should be much less than delta Vd times Id over Vt, right? Which essentially means that this goes off, one of these powers go off, one of these powers goes off, which essentially means delta Vd has to be much less than twice the thermal voltage, right? So for a forward bias diode, your small signal approximation of a forward bias diode as a resistor will hold as long as the incremental voltage, as long as the incremental delta VD is much lesser than the thermal voltage, twice that of thermal voltage, which is approximately 52 millivolt at room temperature, right? So note that this is the case for a diode. If tomorrow you are faced with a different nonlinearity, right, which might not be exponential, which might be polynomial or logarithmic or something else, you will have to redo this analysis at least once to understand under what condition this under what condition the approximation, the small signal approximation will hold, right? So this small signal approximation, this is the condition of small signal in a forward biased diode. Correct? So similarly, if tomorrow you are faced with a different device which has a completely different set of nonlinearity, you will have to do this analysis yourself once to establish under what conditions this your small signal approximation will hold. Okay? Okay, great. So now, by now you must have have understood that in order to figure out the total currents and the voltages in a nonlinear network, we need to follow three-step process. Step one is find out the quiescent. Step 2, replace the quiescent with their incremental equivalent and then find out the incremental currents and voltages. And step 3 is to add up the quiescent and the incremental equivalents to get the total currents and voltages, right? So as it turns out, instead of writing this delta V, delta I or total V every time, there are certain notations that are used in literature, and we will also follow the same notations, and the notations are as follows. So let's say I have an element, and let's call this terminals A and B, right? So if I am trying to denote quiescent voltages or currents pertaining to this element, that is, if I am talking about quiescent current or voltages, I will denote them as capital I subscript capital P AB or capital V subscript capital AB. If I am talking about incremental currents and voltages, instead of writing delta IAB, delta VAB every time, we will be using small I subscript small ab or small v subscript small ab, and when we are trying to find out the total currents and voltages, instead of every time writing as total I, total V, we will follow the notation that is total is small I capital subscript or small v capital subscript. Okay, so please make a note of this, that we will be following this type of notations. Sometimes you will see that it's not possible to follow these notations all the time. If, for example, instead of AB you have 1, 2, 3, right? So in those cases, we will try to denote, we will try to differentiate incremental from quiescent by using either delta or total or something, right? But in general, we will be following this and these nomenclatures. Okay. So till now, we have been in search of uh, an amplifier, right? And uh, we have been doing all these nonlinear analysis or setting up a framework uh, to analyze a nonlinear network, because the ultimate goal is to make an amplifier, right? So let's go back to uh, our original problem statement. That is, I have a source with some resistance, source resistance Rs, and I have a load RL, and we would like to put something in between, right? Something in between, so that I can transfer, I can get a power transfer between the source and the load, right? And what is this stuff in between that we needed to put? We established that we needed a power source, right? We needed a power source somewhere, right? So let's say I required a power source, an additional voltage source, okay? And this additional voltage source, let me refer it to some common terminal, some ground, and the stuff inside the box had to be non-linear. So this was the bare minimum requirement, correct? But note that, I mean, the stuff inside the box cannot be floating. It should also have, it's a two-port network, right? So it should have another port that is coming out. And what should I connect it to? In general, this network, I can say that the voltage source is connected between one port, and the load is connected between another port, right? And maybe there is a voltage source, there is a DC battery which is connected between one of the nodes. One might argue that this DC battery could have been connected to the input side. Yes, absolutely right, right? One might argue that there can be multiple DC batteries, one connected to the input side, one connected to the output side. 100% true, right? Any of those combinations can be correct. We are just taking an arbitrary example. Okay, so let me call this VDC. Okay, so since we have a two-port network, we need to denote some terminologies, right? So let me call this initial port, first port 1 dash, other port 2 dash, and let me call this VDC port as 3, and one might argue that why didn't I give VDC a dedicated port? Why only a terminal and the other port is shared? Well, I mean, we can as well do that, right? Without loss of generality, we can as well do that. Let's give it a port. So 3 dash. Okay, fine. So what can I, from whatever we have done till now, right? From whatever we have done till now, what should be the way forward? Firstly, we need to know what type of nonlinearity that we are dealing with, right? So it's a nonlinear network. Let's say that this nonlinear network is let's say this I1, that is, this is current I1, this is current I2, and this is current IDC. Okay, so let's say the current I1 is some nonlinear function f1 of the okay, so now we are in trouble because we just now established some nomenclatures. So let me follow the nomenclatures. Let's say that this is A dash, this is B dash, this is C dash. Okay. So let's say this current I1, right, is a function of B A dash, B dash, C prime, which in this case is actually equal to PDC, right? Similarly, let's say I2 is another function, nonlinear function F2 of V A prime, V prime, and PDC, and similarly IDC is also a nonlinear function F3 of V A dash, V dash, PDC. Okay, fine, great. Now among these voltages, right, the port voltages, which one do you think is changing as the input changes, and which ones do you think are not changing as the input changes? Clearly these VDC terms are constant, right? These are not changing, right? And in most cases, in most circuits, the DC voltage sources are supposed to hold the voltages constant, right? So they don't change. So essentially they act as some sort of parameters. And which currents are of our interest? Clearly the currents I1 and I2 are of our interest, right? The IDC is a current that is flowing through the DC voltage source. Even though we are calling it IDC, but note that the value of IDC is not fixed because it is a function of the voltages of all the terminals, right? So IDC need not necessarily be fixed. However, at this point at this juncture of our analysis, we are not particularly inclined towards figuring out what's going to happen to IDC, because our main interest, right, is to figure out what are the consequences of, or rather what is the relation between I1 and I2, because if I can figure out the relationship between I1 and I2 in terms of VI, right, ultimately then I should be able to figure out what is the relationship between the input and the output voltages, or in other words, I should be able to figure out what is the gain of this system, right? So essentially our goal is to concentrate on finding out what are the relationship between, what can we do about I1 and I2. Okay, so let's see what can be done. So I1 is F1 of V dash, V dash, and VDC, but note that VDC doesn't change, right? It's kind of a parameter which doesn't change, so I'll just drop it from the argument terms, right? and similarly I2 becomes F2 of VAA dash and VB B prime. So in other words, what are we saying? We are saying that we know that there are DC voltage sources, right, available, but for the purpose of we know that there are some DC voltage sources available and this network is nonlinear, but for the purpose of our analysis we'll assume that these currents that are getting set up, these currents I1 and I2 that are getting set up between these ports have somehow been set up by the DC voltage sources that are there, right? And that is contributing to I1 and I2, and we have figured out those values numerically or graphically or using simulation or somehow, right? But note that we are interested in figuring out what if there is an increment, in these values of VAA dash, right? How does that increment translate to the output, or in other words, how does that increment translate to the increment in the voltage at the across RL, or rather what is the change in VBB dash, right? And what do we want to relate that to? We want to relate that to the input change, the input voltage change DI. Okay, so in order to do that, we will resort to the same old methodology. That is, we assume, right? So under quiescent condition, what is the case? This is your quiescent condition. Under quiescent conditions, you have I1 and I2. Then you add some perturbation to the network. How are you adding the perturbation? We are adding the perturbation by adding an input, adding a small voltage source, right? What is small? Again, it depends on what type of nonlinearity that we are dealing with, right? So once we perturb this, what's going to happen? This current I1 is going to change, right? This current I1 will change by delta I1, or let me simply call this small I1, right? So this voltage AA prime will also change. So let me just simply write this. So my I1 will change from I1 to small I1 because my inputs VAA prime changed. Similarly, the port voltage VBB prime also changed to. Note that we don't yet know what VAA prime and VBB prime are, right? We don't yet know what these port voltage increments are. These are still unknown, right? These are unknowns. Even this I1 is unknown, right? So we are trying to develop a framework for this two-port network, right? We had developed this framework for a normal nonlinear network with one nonlinear element. Now we are trying to develop a framework for this two-port network. Okay, so what should we do in this case? We should simply do the same thing as we did earlier. That is, we expand this in Taylor series around the quiescent condition. What is the quiescent condition? Our quiescent, this is our quiescent network, right? This is the quiescent network. So around the quiescent network, we need to expand. Around the quiescent conditions, we need to expand this nonlinear equation if we expand F1, what should we get? We should get the original term F1 of VAA dash VBB prime plus the increment VAA prime and the derivative of F1 del F1 del VA prime, correct, around the quiescent VAA prime VBB prime plus V B prime del F2 del V prime around the quiescent point plus higher order terms. Correct? So here I get I1 plus I small I1, and we see that these two are identical, so they go off, right? So what are we left with? We are left with the incremental port current I1 is related to the incremental port voltages VA prime and VBB prime. How? They are related as the derivative of del F1 del VB around quiescent operating points times the increment VAA prime plus the del F1 I think I made a mistake here. This should have been del F1, right? Because ultimately we are dealing with a nonlinear function F1, not F2. So this should have been del F1 del V prime around operating points VAA prime VBB prime times VBB prime, right? Similarly, if we do the same thing for I2, right? So this I1 is something that we did this equation that we got here right now that we are staring at in front of our eyes is essentially relating the incremental current at port 1, right? Incremental current at port 1 if there is an incremental change in the port voltages AA prime and BB prime. Similarly, if we follow the same set of arguments for port 2, I should be able to relate the incremental current at port 2, that is, this was delta I1, right? If we want to write this in terms of deltas, so this is delta I1, this is delta I2, which is being expressed as I2 will be del F2, the second nonlinearity, that is the nonlinearity associated with port 2 or the currents in port 2 times VAA prime plus del 2 del VB prime okay. So again, to state the obvious, what is this set of equations, these two equations pointing to? These two equations are essentially saying that if I have replaced all the nonlinear elements inside this network with their linearized equivalent, right? If I have replaced all the nonlinear elements inside the network with the linearized equivalent, and if we had or in other words, this is all this is saying is that this is terminal A prime, this is terminal B prime. We have this current I1, this current I2. All this is saying is, if this voltage got perturbed by from VAA prime to VAA prime plus V small a prime, and the voltage at the other port got perturbed from VBB prime to VBB prime plus an increment, the current I1, right, would have been perturbed from I1 to I1 plus small I1, and the current I2 would have been perturbed to I2 plus small I2. And the relationship between these small I1 and I2 and VAA prime and small VB prime are being depicted by the two equations above, right? So in other words, the incremental equivalent of this two-port network if I simply say that this is VAA prime and this is VBB prime, this current is I1, this current is I2. I can express I1 as some constant times VAA prime plus some other constant times VBB prime. Similarly, I can express I2 as some constant times VAA prime plus some constant times VBB prime. What are those constants? These constants are nothing but the derivatives of the nonlinearities. These constants are nothing but the derivatives of F1 with respect to the port voltages or F2 with respect to the port voltages, right? And note that these derivatives are constant because they are fixed once you have fixed the quiescent voltages, right? Just like in case of a one port network or a single nonlinearity, the derivatives were a function of the quiescent operating conditions. Similarly, in this case also, the derivatives will be a function of the quiescent port voltages and currents, right? So since these are constants, we express them in terms of, there is a terminology associated with them. So we call this is as Y11, we call this as Y12, we call this as Y21, we call this Y22. Okay. And why do we do that? Because this is a standard terminology for an incremental two-port network where we are able to relate the currents, the excitations at the between the port, the incremental excitations of the port voltages with the incremental excitations of the port currents, right? And I am sure you must have done some sort of two-port network analysis in the past, and this is essentially an extension of that, right? And how do we go about doing this analysis of this two-port network? Let me write it out once again. So these terminologies of what is 1, what is 2 has its genesis in the following. That is, instead of writing those terminologies, those ports as A dash and B dash, if we simply say that let's say VA dash is equal to V1, right? So we call this port 1, right? So if we call this as port 1 and this voltage as V1, and if we call this port 2 and this voltage as V2, then VA dash becomes V1, VB dash becomes V2, right? This incremental current through port 1 is I1, and if we denote the incremental current through port 2 as I2, right, then what we are essentially saying is I1, there is some relationship of I1, some linear relationship of I1 with respect to V1 and with respect to V2. Similarly, there is some linear relationship between I2 and between I2 and V1, V2, and these constants, these proportionally constants, we call this one as Y11, this one as Y12, this one as Y21, and this one as Y22. Again, why this is why are this called as Y11 and Y22? Because what is the, how do you get Y11? So what is the definition of Y11 from these equations? From these equations, Y11 is equal to I1 over V1 when V2 is equal to 0. Right? Right? In other words, so this is in plain English, this means the incremental Y11 is the ratio of the incremental change in I1 with respect to incremental change in V1 when V2 is constant. So this part is vital. V2 is constant, right? So when V2 is constant means what? Means small v2 is 0, correct? And since when small v2 is 0, why the relationship between I1 and V1 is simply I1 equal to some constant time V1, and that constant we relate it as Y11. Okay. Similarly, what is Y12? Y12 is nothing but Y12 is I1 by V2 when V1, small v1 is 0, which means the voltage across the port V1 is held constant, right? Right? So note that this first term, this one relates to the excitation that I am interested in the port number that I am interested in, and the second term 2 relates to the excitation, the dependent variable, or rather the excitation with which I am taking the derivative. Similarly Y21 will be I2 over V1, right? I2 over V1 when V2 will be equal to 0, and similarly Y22 will be I2 over V2 when V1 equal to 0, right? So in other words, to make it explicit, V2 is constant when V1 is constant. So these are the ways, these are the definitions of y12, y1, y11, y12, y21 and y22. Okay, so we'll stop here and we'll start off in the next class.